there. So I'm sharing the screen, this one here, there. Okay. So the simplest case would be, for example, if you choose or if you have a uniform distributed force, okay? And of course, that's the simplest case. Yeah, you can immediately imagine what could happen if you have a different force. I mean, it's just integration, and I understand you can integrate. Okay, we can say, if I can find my pointer, here is my pointer. For example, for the uniformly distributed force. Okay, we say, for example, Fx is equal to, I'm sorry, let me write like this. Okay, it's just a constant. Okay, and so we have that Fi, Fj, and Fk. So it's equal to the constant is out of the integral, and we integrate from 0 to L. And here we have Ni, we know that is equal to 0, and J, that we know that is equal to 1 minus S over L, and then K is equal to S over L ds. Everybody, not everybody. Let's see. Okay, Mr. Diaz, could you integrate the second? Mr. Diaz, Big Mar Diaz, you integrate this one here. And Ms. Vega, please integrate the last term. So Mr. Diaz, integrate this, and Ms. Vega, integrate this, and give me the values, please. Mr. Diaz, are you there? Mr. Diaz?
Yes, sir.
Okay, please integrate this term. And this is going to be integrated by Ms. Vega. So the result is going to be, of course, 0 for the first one.
One over 2.
L over 2, because it's integrated in L. L over 2. Ms. Vega, what did you get? Ms. Vega, are you there?
L over 2.
Exactly. Make sense? Yeah. Yeah. I mean, if we have something like this, right? If we have a uniform force, this is the situation that we are analyzing. And you're telling me that the total force is going to be FL, right? And then you put it half on one end and the other half in the other. So you're saying that you transform this into that. So this is FX, L divided by 2, FX, L divided by 2. Make sense? Yes. But now you can proceed, we can apply this procedure and analyze any distribution that you can have. Questions about this, people? Questions? Questions about this? No questions? Okay, so you see that this procedure is very similar, or it's the same procedure. The only difference with the previous one is that in this case, instead of worrying about 2, we have to worry about 3 joints, that's all. But because of the interpolation function, it's a linear, you see that in one of the functions, which makes sense, do not participate in the integration. You get simply 0. That's it. Makes sense because...
Doctor?
Yep.
I have a question.
Yeah, go on.
What happens if we have a several combining of the triangles along one edge, for example?
What you can do, you can do one at a time. Okay, let me try to. Okay, let's suppose that we have, for example, a more elaborate situation. So, for example, we have something like this, and we have something like this, right? So what we can do is we can discretize. So this is our discretization. Now we go on. So we, instead of this distribution, we're going to have let's worry about only f in the x direction, okay? So we take in this element, we have this distribution. So we're going to have, since this is closer to this, probably we're going to have a larger force in this joint and a smaller force in this joint, probably. And this is the result of considering this line, this side of the triangle. Now we have to consider this. And in this case, let me change color. We do the same procedure. And since it is pointing to the left, this one here, and closer to this one, where this is more to the right or to the other joint, right? So probably if we do this for this concentrated force, we're going to have something like this. And if we do this integration for this joint, considering both, since this is closer to the end, we're going to have something like this. And at the end, we're going to have, in here, I'm going to have 2 values, but with the opposite direction, you have considered the combination of the 2. You go one element at a time. Probably you see that in the CST program. You have to specify the distribution of forces in every side. Go on.
So for that situation, for example, when we have various elements of triangles or plate with large dimension, we need to, the advantage for that situation is the symmetry, right? Because, for example, when we have a large or big plate, so there is a lot of work for one by one.
Yeah, but the thing is that we can push working in the way I've asked you up to a certain point. I don't expect you to include 200 elements because that's just too much. But it's always a good idea that you have in mind what discretization means, not in one, but in 2 dimensions. That's what I'm asking you to do. If you want to go to a larger system, more complex system, geometry or whatever, in that case, that's the next step. We're going to show you how can we use a commercial package, in this case ANSYS, in order to solve those problems. And the thing is that you put information and all these calculations are completed inside the computer program. You don't see them. But if you do this before, you have a decent idea of what's happening inside the program, inside the computer. So when you start having results, you can start thinking, okay, so this is what it did. This is what it obtained. Does that make sense? If that doesn't make sense, then you have to go back and check your data. And the only reason you can do that is because you understand, you have a general idea what's happening inside the program. That's what I make you to do this using this low-level program. Okay. Anybody else, please?
I have a question, doctor.
Go on.
I am a little bit confused in your slide 13 when you obtain the equivalent forces, Fx and Fy, in the slide 13.
13, okay.
Yes.
This one. Yeah.
Is that I am really confused because you put that we are going to have Fy and Fx, but in the plane stress, we don't only consider the Fx force.
No.
The Fy not act like a
No.
not
No.
influence
No.
in the bending.
No. Remember, see, this is plane stress.
We need to obtain Fx and Fy.
Exactly. This is plane stress, okay? Let me go back. Let me go at the beginning. Don't go, we're fine. We're trying to solve here. This is plane stress. This is what we're working, plane stress. So we have a structure which has dimensions, which are very important, not only in the X direction, but also in the Y direction. The third dimension, the thickness, is very small. Okay, so in that case, we can do the simplifications that sigma z is neglectable, that tau xz and tau yz are also neglectable, and we can analyze this with only 3 elements, with the elements of the stress tensor. But this structure is in the XY plane. So we can apply, let me include here, we can apply another force in the Y direction with no problem. I can apply a force like this because it's in the plane. Okay, so if you apply these type of forces, you can expect that any point on the plate to move in the X and in the Y direction. What you cannot expect is that this point moves in the vertical direction. That's for the other type of problems, that's the bending. Yes. So you could have any force in the plane, in the X and Y. So you can have forces in the X, in the Y, and also shear in the XY direction. What you cannot have is forces in the vertical, in the Z direction, because that produces bending. And that's something that we are not including in this analysis. Misayo? Okay, no problem.
Yes,
no problem.
No problem. Thank you.
Okay, yeah, probably. Yeah, let me explain a little bit more about that, because okay, here. Here, whereas the example that I presented in the previous slides was, see, was a plate like this. I'm going to draw it in the, without AutoCAD. Okay, that's the plate that we analyzed it. It was clamped here, and we have a force, a vertical force in this case. This is the example that we analyzed, right? So in this case, well, we said, okay, this is our x-axis, this is our y-axis. So the plate supports forces in the plane. So this is one case that we can analyze. So we say, okay, we're going to look at like this. This is x, this is y, and this is the force. We could also apply a force, for example, here, like this. It's going to be an fx. And we can analyze this case with this chapter. Why? Because forces are in the plane. So both cases are okay. Because I insist, the actions, the external action are in the plane, in the XY plane. So everything is fine. Now, this case, the case that I presented here, is very interesting because it represents the bending of a cantilever plate, right? And the thing is that in this case, okay, we are not assuming the kinematic hypothesis. See, when we analyze this case, okay, this case, we didn't say epsilon x is proportional to the vertical distance. We didn't say that. We only said, okay, we're going to take this and we're going to try to find the minimum potential energy. And that's associated with a static equilibrium. That's the only thing that we said. So you can go on, for example, and you can include a very good discretization. Okay? And you can calculate, for example, the axial displacement of this point. You can calculate the axial displacement of this point, the axial displacement of this, the axial displacement of that. If we follow the kinematic hypothesis, that's solid mechanics, bending of beams, then this the axial displacement of these points must follow a straight line. In here, not necessarily, because we are not assuming the kinematic hypothesis. So that's why this example is so interesting. Eventually, we could go on and try to make a very small partition. And the results are supposed to be close to the pure bending beam problem. Close. Why not? Why not add exact? Because in this case, we also include shear stress. So it's kind of similar, but it's not exactly that. Because in here, we include the shear deflection. That's the reason because I included this example in this class notes. Ms. Sayo? Ms. Sayo, did I answer your concern, your question?
Yes, doctor. Yes.
Okay. Are you here or in Machala?
I'm here in Guayaquil.
Good.
Yeah.
Okay. Anybody else? Any other question, people?
Doctor Carrillo.
Go on.
For example, I have the in position X, L, in this sample you have this moment.
Okay.
In position X, we have the chain design, the stress for more than 2 occasions.
Would you repeat that, your question, because I couldn't.
For example, I have position in X. It's possible I have the structure and the stress, the chain design. More 2 occasions.
This is an approximation. And what you are going to obtain are the stresses in every element.
Yes.
If you need more detail, for example, around this point, it's a very important area, because in this area, you're going to have the application of the force. So what finite element give you is the possibility of flexibility. So if we are interested in this area, we could use a different partition which uses smaller elements in this area. In this case, I have one value of the stress in this element, another value in this point. So you can describe in a better way the distribution of stress in this area. And the elements, as you can see, they don't have the same dimensions. So it's quite flexible. And the idea is that you remember that what we are doing is we partition in every element, we have a linear distribution of the displacements. And from that point, and you go on and set up the equations and all of that. But you have the flexibility of discretizing the structure in the way you need. Carrillo?
Yes.
Okay.
Doctor, you have the one, for example, force equivalent. We have only, we have the project, we only have the force in X, no more.
Okay.
The moment, no.
No, in this case, no. In this case, no.
I thank you.
No problem, no problem. Because in this case, we are not taking that representation. But if you want, for example, in this case, okay, in this partition, okay, about here, probably you're going to have a tensile stress. In here, you're going to have a tensile stress smaller. In here, probably you're going to have a compression, I don't know, maybe it's tension or compression here. I don't know what. Let's suppose compression and compression. And we can take this, make a cut here. Okay, let me just assume this cut here is this cut here. So we're going to have a joint okay, so from here to this point here, you're going to have positive stress. So it's going to be like this. In here, in this little space down here, you're going to have a different stress. Then here, it's going to be very small. Then down here, you're going to have probably negative. And in the last part, you're going to have a larger negative force. Something like this. So I'm showing you sigma x, and this is the y position. Now, what you can do is you can calculate the force because of these stresses, force of these stresses, force and force. And from all of these forces, you can produce a bending moment. You can estimate the bending moment that is produced in this cut. But you have to integrate that because this is not beam theory. In beam theory, you solve the problem, you take the second derivative, multiply by EI, and that's the bending moment. In this case, no. Because in this case, we are not assuming kinematic assumption. This is a 2D problem. The beam is a 1D problem. Okay? Also, you can, for example, you can integrate this and you can add 1, 2, 3, 4 forces. And the value of that should be 0. Because if you make a cut here, you see that I have a vertical force downwards. So in this cut, there should be no net axial force. So these two must be equal to those two and cancel to 0. They are not precisely equal to 0 because this is just an approximation, but should be 0. See, all of these implications, we can accept them because we are discretizing in the 2D problem. But yes, we are not going to have directly the moment because this is not bending. This is just plain stress. But we can use it to analyze a different problem in a more deep way. Because here we are not assuming the kinematic assumption. Anybody else, please?
Doctor, I have a question.
Yeah, somebody, Galarza, go on.
Yeah, if I want to analyze the stress in the graph that you have in the right-hand side.
This one here?
Yeah, in the line, in the right line.
Okay.
I want to analyze the stress along this line. The program will give me the stress for each element, right?
Exactly.
So I can add all the stresses for all the elements in that line and then give the average.
Yeah. Well, that's one thing. I mean, we're going to talk about that in a minute. Okay. Yes. For example, let's suppose that we have a plate, and let's suppose that I pull it from here, and you have a discretization. If I make a cut here, okay, this cut is this one here. I'm going to have a distribution of stress like this. It's not going to be uniform. Why not? Because the force is concentrated in the central part. So from here, I can calculate an average stress. And this average stress should be close to F divided by A. That means that this part is in equilibrium. Because if I make this analysis, I will have F. This is a negative phase cut, so the tension will be in that direction, and this is going to be equal to the average, this value here, times the area. See, there's nothing else, so this should be in equilibrium. So this average should be very close to F divided by A. If you make a cut in a different position, the distribution will be different, but the integration should be equal to F, because you can do something similar to this, and still you have to have equilibrium. So instead of this, you make a cut here, you still have to have this piece in equilibrium. So the average stress in this cut has to be equal to F over A approximately. Galarza?
Okay, doctor, I got it. Thank you.
No problem.
And after that, we can calculate the stress concentration factor.
Exactly. That's the idea. Okay. For example, you can say that I have this situation, and I said, okay, if F over A is below 235, we're fine. And that's not correct, because if you get a B here, and you make a cut, for example, at B over 4, okay, this value of this distribution is going to be like that. So this is the maximum stress that you're going to have. So this value is the one that you have to consider, not F over A, this value here. And that value is going to be a percentage, a number, multiplied by the average. And that's the definition of the stress concentration factor. So we can calculate that using finite elements and compare it with the tables that we have available in the literature. So what you have to do is you have to consider cuts at different distances from the end, and they will give you the maximum stress as compared with the average one. And you can compare those values with the one that you obtain using your results.
Right. Thank you.
Okay. So we're going to go to the next break, and I'm asking Ms. Genesis to break up in groups from 1 to 12, I think. And then when we return, Engineer Isaac is here. Engineer Isaac, okay, and Genesis. So Genesis will be working with groups 1 through 4. Isaac will check in groups from 5 to 8, and I will go with groups 9 to 12. Okay, so we want you to show us what you have done so far and how have you organized the next levels of work. If you have any doubts, now's the time. If when we get together, we will have maybe some common questions and I'll try to answer them back. Okay, so I'm going to send Genesis and Isaac some questionnaire so you can ask those questions to each one of the groups. And then we're going to be back by, I'm going to go because I need a break for my throat. And when I return, I'm going into group, talk to group number 9. The same with Genesis and Isaac. And we have to be efficient because we have half an hour. And when we return 8:55, so we have about 20 minutes to do this exercise. When we return, if there are common questions, then I'll try to answer back. Okay? There's no time to waste. So let's take a break. And please, Genesis, go on with the partition. And I'm sending you using email the questions. Okay?
Okay. No.
Oh, they already assigned it. Good. Thank you very much. This is very efficient. So people, can we send them to the group? Yeah, they're going to the groups. Okay, good. Okay, good. Thank you. I'm sending you right now if I can find my email.
Right?
Exactly, the Excel.
Okay.
Remember that we are short of time, so we cannot lose any time. Check if you receive it and let me know, please.
Doctor, you have to make the engineer Isaac
Okay.
host.
Co-host. Okay, so Isaac, you're co-host now also. So you can go on and check and work with the groups. Okay, go on, please. There are some people who still in this room. Can you send them?
Doctor, I check the group for from what?
From 5 through 8.
5 to 8. Okay.
Yeah. Genesis from 1 to 4.
Yeah. The people that are still here is because they didn't accept the join, but the message is on their screen.
Yeah, please, people, accept to join your group and go on and start working with the group. Don't waste any time, please. Okay? Okay, I need a break. Okay, Mr. Barba, can you hear me?
Yes, sure. Good morning, doctor.
Good morning. Besides you and Freire, who is the third member of the group?
Matute.
Who?
Matute, Ronnie Matute.
Matute. Okay. Who is responsible?
Matute.
Oh, man. Okay. What have you done so far, people? Have you run the program? Can you turn on the cameras if you can, please,
Yes.
if it is possible?
Yes.
Okay. What have you done so far? Did you run the program already?
Yes.
Okay. How many times? How many models?
2 hours.
How many joins? Or how many elements did you include?
I wrote
I cannot hear you.
39.
39. Okay. 39. Is that good enough or?
Yes. Yes. But also understand define the dimension.
See, the thing is
Because,
this, okay? The thing is this, okay? And what's the problem that you have to solve?
Case 1.
Case 1. Let me try to find out case 1. Okay, class notes. Okay, in case 1, remember that you don't need dimensions because what you need is a ratio. Okay, it's a ratio between dimensions because that's the ratio between dimensions influences on the increment in stress, and that's what we need. We don't need an absolute value. We need how much increases the stress because of this concentration factor. You said what case?
1.
Okay. So you can take any dimensions, right? The thing is that you have to follow the restrictions. Okay. And of course, the area, when you have this change in section, okay, that's the most important part. Did you find a reference to compare your results?
No.
No, you should look for that, okay? Probably look for in Popov's book, okay? Because the idea is that you calculate that using finite elements and then calculate using, or compare that with the things that were available in literature. Okay, Ms. Freire, what have you done for this project? What was your contribution for this project?
So far, I have helped in the. I mean, we all get in the Zoom session to discretize the element and to try to understand this structure of the program.
Okay.
But like individually, I haven't done so far anything.
Okay. How many Zoom sessions did you use? Have you taken? Have you had?
Two. Yesterday and on Tuesday. Yes.
Remember that everybody should understand what the process is, because in the evaluation, you're going to be separated. So everybody will be evaluated. So try to to have that in mind.
Okay.
Now, and in the if for the complete this assignment, when are you going to keep working? And Mr. Matute has done anything about this, or
Yes,
Oh.
yes,
so the three are working together?
yes.
Okay, good.
Okay.
So when are you going to meet next?
And today at night, around 7 p.m., we're planning to continue.
Okay.
And also to start the report, because that is also like
I changed that. The due date now is not next Monday, it's next Thursday. I guess you know that, right? So I give you 3 more days to complete that.
okay.
Okay. Okay, good. Please, I wish I had some more time in order to see what you have done, but I don't. Okay, so please keep working on that, okay?
Okay.
Remember, in about 10 minutes, 15 minutes, you have to return to the main session, okay?
Okay, doctor. Thank you.
Bye-bye now.
Área de plan, creo yo.
Okay, Mr. Carrillo Mateo, who is missing here?
Doctor, good morning.
Good morning, doctor.
Good morning. Mateo, that's not your last name, right? You are Mateo Wacon, right?
Yes, doctor.
Okay, and who is missing here? Who is missing? There's only 2 or there are 3 here.
The other parent, why is no Mateo?
Who is missing?
I don't have remember story, doctor. This is moment my parent is work.
Okay, who is responsible for this group?
Me, Doctor Carrillo.
Okay, what have you done so far? I mean, did you run the program?
My parent, Mateo, have doing program is.
Okay, go on.
I took charge of the program.
How many joins, how many elements did you include in your model?
48 and 96.
9 joins.
Joins is 38.
One model, only one model.
Yes, is
38 joins. Okay. And how did you organize these things? I mean, did you work on Zoom sessions or what?
I begin the work and analyze for the elements. Have the disk size, determine the different value of the stress. My parents is the Mateo is the program. The other parents, I don't have this moment. This is the begin the work and the report.
Okay, but you have to be careful because when we evaluate you, okay, everybody should be able to describe how to use a program and this or that. Okay, so be careful because it's a good idea that you organize your work, somebody do this, somebody do that. But at the end, everybody should be aware that must understand the whole thing. Okay?
Yes.
So please be careful with that. For example, using the program, discretizing, things like that, you should be able to everybody should put some time on that to understand the process. Okay? What model did you have to use? What case do you have to analyze?
Second case, doctor.
Which one?
Second.
Case 2, okay. Okay. So did you get any references? Did you find any references to compare?
Class no, doctor.
Now you have to find it, okay? Because the idea is that you calculate using finite elements, and then you have to compare with some published results, okay? So it is possible, for example, that in Popov's book, you can find something. Another reference that you can find, where you can find this, is Roark and Young, R-O-A-R-K, Roark and Young. These are two authors. They have a manual with many situations, and they present information about concentration factors. Okay?
Okay.
Try to find it, but because the idea is that you calculate and your result, you compare it with these other references. Okay?
Thank you.
Yes.
Okay, remember that I'm giving you in case 2, and in case 2, so you have the ratio B over R between 4 and 4.5, but you have to have at least 3 combinations, maybe 4.25 and 4.5. Because we like to see how these different values of the ratio give influences on the final results, okay?
Yes, doctor.
Okay, when are you going to meet? The next meeting, when is it going to be? The next meeting, when is going to be?
In 3.
Okay, 3 p.m. When are you going to meet? When are you going to meet? People, tell me.
In soon, doctor.
Yeah, when? What day?
Thursday, Wednesday, Monday.
Thursday, what? What else? Thursday?
Monday, Tuesday, Wednesday.
Okay, people, don't get late, okay? Be aware that...
Doctor, I see example for the program in Darcy Logan. It's correct.
Okay.
Can have a reference with the book.
Yeah. But the thing is this, okay? Right now, basically this one reference that I have to see is the reference where you have taken the values of the concentration factors. That's the most important reference.
Okay, doctor.
I can give you, I think I published in the very first session, I included as a reference the book, Logan's book.
Yes.
So there it is, the exact title, the author, the year of publication, and all of that. But the most important reference is the reference where you have these values of the stress concentration factor, and you compare. Okay, I have to go now.
Thank you, doctor.
Okay. Diaz and Nevares. Is there anybody else here who else is in this group? Who else is in this group?
Karen Combe. I don't know if she's trying to
to get in.
Okay, and who is the leader responsible for this group?
Hi, doctor.
Who? Diaz, are you responsible for this group?
Yes.
Okay. Okay, did you run the program? Did you complete any model? How many joins did you include in that model?
In the model of my case, or
Yeah.
Okay.
How many joins did you have?
15.
15, that's not much. It's a small model. You have to include more because with 15 joins, I mean, the elements will be very large. So the results are not going to be very good. So you have to include more. Okay, and the results, did you analyze the results? Did you
No,
have the
doctor.
time?
The result, no, because they have a little problem with we compare in Spanish, comprehend the force, because I think that the axial force in the side, right? But in one class you explain one exercise that the force in downward, but when have the two joints, the force divided for two.
Okay.
In one point my question
But
is
the thing is this. The thing is this. The thing is this. You can apply any force that you want, any force. Because what we want is the ratio between the mean stress, okay, and compare that with the maximum stress. So for example, you take advantage of the symmetry, right? So you apply a half force. Okay, how much is that? 100, fine. So you take 100 divided by the area, that's the average stress. So what's the maximum stress in this distribution? This much. This value divided by the mean, that's the stress concentration factor. That's the number that we want to check. Okay?
Okay.
So the value that you apply, the value of the force that you apply, it's meaningless. Why not? Because we take the average, the ratio. Since this is a linear problem, okay, if you increase the force, both will increase, the numerator in the denominator. So the quotient doesn't change. Did you find any reference to compare? Any reference? Where are you going to obtain the value of, what case is yours? Case what?
Case 3.
Case 3. Okay, what you can do is you can make a cut, okay, at B/4. That's a good value. And check out in Popov's book, okay, there is a good graph where you can find the maximum stress at this cut, B/4. So you can compare your results with those from Popov's. Okay, they show a curve with the distribution of the stress in the vertical direction. And of course, the maximum value, which is the most important, at B/4. So you can do something similar. Make a cut at B/4, get those values, plot them, and compare with Popov's. So that's the main reference that you need to mention. Okay, people, please. I notice that you're a little bit behind. Okay, so please put more effort on that. Okay, let's return now to the main room, please. Okay, please remember that we have to worry about a convergence And for that, you need to use a decent number of elements. Okay, so please, you have to put effort on that. Also, all examples has some sort of symmetry. All examples, all cases. So try to take advantage of that. I am not going to tell you how to do it. You have to think. Okay, if I make a cut here and consider only half, what condition do we have to apply here in order to make it believe or get the results in this area equal to those results in this area? So if I get the same results here and there, I can make a cut and analyze only half. So the number of joints that I have to define, the number of elements that I have to define, I just cut by half. So that's a good idea. It's a good advantage to take off. So please take advantage of that. Okay? Remember that we have to compare, and we have to compare with a reference. And that's the reference that I want to see in the report. Okay? If you find more than one reference that presents the values of the concentration factors, that's fine. But at least one. Okay? I mentioned to one of the groups that a good reference for this information, concentration factor, is a manual from Roark and Young. I'm going to write it in here. If I can find it here. Okay. In my time, probably I used one of the first editions. Now there are many. And the thing is that try to find one of those versions, okay? See the geometry and get the values of the concentration factors. Another good reference for this, very simple, is the reference from Popov's book, okay? There is some very simple explanations about concentration factors, and they present, for some cases, not for all, information about it, okay? In the case 3, when you have the plate, okay, with some tension, okay? I think Popov's book present this distribution, this plot at B/4, okay? So you could take this graph from Popov and you can plot in the same graph with your results and compare the maximum stress or the stress concentration factor if you want, okay? And the idea is that you compare, I insist, the maximum value with the mean value. That's what you have to have in your mind in order to avoid failures. I changed the due date for this project. Instead of being next Monday, it's going to be next Thursday. Okay? Any question, people, so far? Unfortunately, I didn't have time to work with group 12. Okay, who is in group 12, people? Anybody who is in group 12? Who is in group 12? No, nobody's in group 12.
Maybe they're still waiting inside.
No. Oh, yes. Because the problem is I didn't have the time to work with them. Okay. Please, somebody tell them that if they need assistance, they can send me an email. I try to get with them, okay, because I don't have time now. And the problem is that today is going to be quite busy for me. I have to do some personal business in downtown, so I have to run. In the afternoon, I have an appointment at 2, a meeting, a university meeting at 2. I have a class at 4:30. I have at 9 p.m. I have to work with the graduates, the future graduates. So I'm busy. But tomorrow I have time. Okay, so if you want to talk to me, have any doubts, anything like that, send me an email. Send me an email, and we can arrange a meeting on Zoom or something like that. Also, next week probably I will be in the university. For those of you who are here, and you can have time. Yes, we can agree, so we can get together in the university too. In some cases, it's much easier to talk in person. But anyway, okay. Before we break up, please, this is something I want to have you in mind, okay? Okay, this is the second week after the evaluation, right? So here, I have, this is the 3rd, 4th, 5, 6, 7, and exam. Okay? Here in the 4th, in 2 weeks, we will have an evaluation, okay, and project presentations. In here, next week, we will talk about chapter 4. And chapter 4 will be about the geometric modeling. Since you have already experienced using Rhino, there's no problem for that. But anyway, in any case, Engineer Isaac will be explaining you how to use Rhino in order to produce a geometric model of an structure. And then these 2 weeks will be an introduction to ANSYS. Okay, so in here, we will assign projects. If any group has an interest in a certain structure, you can talk to me. And if the structure has enough difficulty, I can let you work with that. Otherwise, we will assign you. What we usually do is we take a full ship, and what we do is we say take a part of the structure and assign it to each one of the groups. Okay? So, and then the 7th week, we do just progress control. Okay, and then in the exam week, we do project presentation. Okay, in here, probably about the 6th week, we have another evaluation on ANSYS. Okay, so probably ANSYS will take us about 3 sessions. Okay, we have already prepared some slides, some transparencies explaining how to use ANSYS. So we can share with you so you can review them. It's so easy, and you can follow the explanation. Any questions about that? So this is very important that you have in mind. Okay, next week we will go to geometric modeling. Then the 4th week you will be here. We will have evaluation on 1 day, and we will have project presentation on Wednesday. So this plane stress, you are going to be here, you are going to present them. And then after we return from Christmas holidays, then we will work with ANSYS, 3 sessions, and then we will have 1 evaluation on that. And then the last week is just progress control. So we would like to see what you have done so far, so nobody can get behind. And then project presentations will be during the exam week. Any question, people? No question. Okay, I'm sorry about this, the 8 minutes. Any question?
For what date is this project due?
Thursday. I changed in the seed web. Did anybody check in the seed web? It's already changed. Did anybody look at that? I already changed. Okay, if there is no more questions, then I'll see. Okay, it's already been changed, right?
Yeah.
Yes, doctor.
Okay, good. So that's it for today. I'm really sorry about these some minutes that we were behind. I insist on those on group 12. If you need, talk to me, send me an email, and we can get together on Friday, because today is going to be extremely, extremely hard for me. Okay, bye-bye now.
Thank you, doctor.
Okay, Genesis and Isaac, please stay in the room for a second. Just a quick. Okay, ¿cómo estuvieron?
You're recording.